Bonus: Chemistry of Salt. Hello, and welcome to this bonus episode of the History of American Food. The 1600s saw a lot of big changes in commerce and chemistry and war. And salt, or I should say salts, plural, had a big hand in all of that. So if you want to take a tour of what salt is generally, how it works, and two particular salt types that were important to 17th century American food, stick around. We'll take another tour of some of the brain furnishings of the past and see what has stuck around into the present day. I did not get this out on Friday like I wanted to. Instead, I got to go to the dentist twice this week because I cracked a crown. I just have to tell you that after studying history and culinary history specifically, I really appreciate modern dentistry. I have a pretty bionic mouth at this point. If I lived in the 17th century, I'd probably be one of those toothless crones. If I hadn't already died from my bout of appendicitis. Oh yeah, I have a couple of those how I would have died if I lived before World War I events in my life. So a quick acknowledgement to the really amazing stuff 21st century dentists can do. The material science that is used there, for a chemistry person, it's pretty much performance art. Okay, back on track. The periodic table. In case you've blocked out every high school science class you ever had, and there are reasons for that I can understand, I'm going to do a very general orientation and explanation. I've included a nice general version of the periodic table in the show notes at thehistoryofamericanfood.blogspot.com, but you can also just do this in your head. There's no real specifics that are necessary. I just still find the thing so dang interesting because the underlying structure was built by guys, and it was mostly guys until it was mostly filled out, who knew nothing about the subatomic structure of atoms, protons, electrons, those things. They did it all by naked eye observations, taking temperatures and seeing what combinations of what burned off their eyebrows or melted off their fingerprints. Okay, I'm being a little silly here. But for me, the coolest part was when they left blank spaces for elements they knew had to be there and left descriptions about things like what color it would be, what temperature it would melt at. Anyway, salt, NaCl, sodium chloride, and salts in general. Initially, alchemists and natural philosophers, these are the guys who were, among other things, purifying their urine in alembics, trying to isolate sulfur, trying to turn lead into gold, find the secret to eternal life, and coming up with bright new dyes that caused the people who wore them to go crazy. Yeah, anyway. When not trying to blow up their houses or poison themselves with dodgy experiments, they did record some interesting stuff and did eventually move alchemy into chemistry. Early on in the project to systematize things, there was an idea that any water-soluble crystal was a salt. So some people actually classified sugar as a salt. It's not. It only contains hydrogen, carbon, and oxygen. And all salts contain a metal half and a non-metal half. But as these emerging scientists started to get serious about recording their observations and actually discussing their ideas, they came up with rules for what a salt was, and then how they could be messed with, and eventually how they could be useful. So let's get chemical. As a broad generalization, on the periodic table, there's a positive side, the left, and a negative side, the right. I'm going to leave out the stuff about electrons and protons because nobody in the 17th century knew about them. And that's not how they were approaching salt, or chemistry in general. Just as with magnets, salts have a positive side and a negative side that attract each other. If large amounts of the pure positive side and the negative side get together out in the air where there's oxygen, it's always explodey and exciting. But if they get together dissolved in water, it's invisible and silent. But watching the crystallization from evaporation on microscope cameras, it's downright mesmerizing. I've put a couple of videos in the show notes for you to check out. So, on the periodic table, sodium hangs out with the other salt-forming metals in the first column, like lithium and potassium. And then in the second column, there's magnesium and calcium. You'll rarely see sodium, lithium, or potassium metals in the wild. They are so toxically positive, they will literally throw themselves at other chemicals to get at and combine with their negative parts, which is what is happening when you put sodium in water. It shoves hydrogen aside just to get at the very negative OH or hydroxide ion. All the bereft hydrogen ions combine protectively with others into hydrogen gas. The sodium forms sodium hydroxide with the snatched OH, and all of this splitting and combining and dissolving gives off a bunch of heat, which explodes the hydrogen gas. Fun fact, the exact how of why this happens is under investigation using computer modeling and high-speed microphotography, like right now. There's always something new in chemistry land. Anyway, explodey. On the negative right side of the periodic table are a bunch of gases. All the way on the right are the noble gases. They don't want to combine or do anything with anyone. So we'll just pass them by, though they do glow very specific pretty colors when you zap them with electricity. The next column of gases, the halogens, fluorine, chlorine, bromine, iodine, American English pronunciation is troublesome, isn't it? Are all negative and are very happy to combine with the super positive metals. And that name halogen, from the start everyone knew they were involved with salts. There are combinations of other nonmetals like sulfur, oxygen, nitrogen, carbon, phosphorus that also like to get together to form negative things that combine with the positive metals to form salt. Okay. So, after some wrangling and discoloration of fingernails, it was concluded by the alchemists and natural philosophers, when an acid and a base are combined, the result is a salt and water. So, if you can get a crystal by combining an acid and a base and evaporating, that's a salt. Now, this isn't usually how most salts are made. Pure acids and pure bases out there in the world are not common, and they don't typically stick around. But it was a good way to create a system. So, hydrochloric acid, which in the language of the 17th century was known as both muriatic acid, acid of the sea, or acidum salis, acid of salt. When hydrochloric acid gets together with sodium hydroxide, which was and is known as lye, it produces sodium chloride, salt, and water. And that's it. These two very poisonous, caustic things get together to produce these two really boring things. It's kind of wild. Other acids, sulfuric acid, nitric acid, carbonic acid, each mixed with sodium, potassium, or calcium hydroxide bases also produce familiar salts. If you want a version of this, you can try at home. Make a salt by mixing an acid and a base. Add vinegar, which is a diluted 5% solution of the weak acid acetic acid, to baking soda, which is the nice weak base sodium bicarbonate, or sodium hydrogen carbonate, depending on how old you are. Chemistry nomenclature is going through another change right now. Anyway, taste them. Sour and salty bitter. These are food. It's okay to put these chemicals in your mouth. These two get together, this acid, acetic acid, and this base, sodium bicarbonate. They get together, they produce water, carbon dioxide, bubbles, and sodium acetate. Sodium acetate is just what they put on salt and vinegar potato chips to give them that salty, sour flavor. So if you mix about 8 grams, which is a teaspoon and 3/4 of a teaspoon, of baking soda and 110 mils, which is about a half a cup of regular white vinegar. If you mix those two together, you'll get pretty close to a complete reaction. Nearly all the original acid and base will get used up. Stir until you get rid of all of the bubbles. If you're feeling really curious and want to check out physical chemistry land, hold your hand to the side of the container you're using or put a kitchen thermometer in there while you're stirring. Now, compare this new mixture to how the original ingredients tasted. It won't taste like either starting ingredient, and it will be at a totally different temperature. Chemistry! It's so cool. I'll explain what the heck happened in the show notes if you're really curious. Now, I also mentioned that temperature and pH. pH is the measure of how acid or basic a solution is. How those will affect how much salt can be dissolved in water and at what concentration it will crystallize out. And then I just ran right on by without stopping. The main reason I did that is because salts themselves can be acidic or basic, and acidic or basic solutions are made with particular acids or bases. Due to the very, very cool, but also very, very complex principle of equilibrium, the amount of a salt that can dissolve in an acidic or basic solution depends on the properties of the salt and the acid and the base being used. See, that just cleared everything right up. Great. Now, temperature is a little easier. Most salts and other things, especially carbohydrates like sugars and starches and things like that, dissolve better in warmer water. The whole thing about heating a liquid to get things to dissolve in it better, that has merit. But of course, because chemistry, there are a few salts that actually dissolve better in colder water, just to mess things up. So when I said there are lots of moving parts affecting the crystallization of salts, what I really meant was people spend their careers, even now, dedicated to understanding the behavior of salts in various mixtures, pHs, and temperature conditions. Chemistry will never be boring, and now it has better has better tools, and you get to keep your eyebrows. Along with sodium chloride or table salt, there's an absolute alphabet soup of options. A few are used in the kitchen, but even more that are mildly to super poisonous are used in other manufacturing situations. Though to be fair, most of the salt used in industry is also just plain old sodium chloride. Salts, especially the ones that were all white crystals, had to be categorized some way other than just looking at them. Tasting was one way, but you had to be careful with that. It could get you killed, either very quickly or slowly and painfully. A much more fun and usually less lethal method was burning a sample of a salt in a flame. Potassium salts give purple flashes. Copper salts give blue and green flames. Lithium is red, sodium yellow, and magnesium salts often give off bright white sparkles. Oh, guess how fireworks are colored, by the way. Now, salt names that are all chemical words like magnesium sulfate or potassium chloride are not how they were known in the 17th century. For the alchemist or dyer or tanner or builder or cook or housekeeper or armorer, these had other familiar, more useful names. And to make it extra fun, one chemical might get multiple names based on how it was made or used. And then multiple chemicals might end up with the same name, again, based on how they were made or used. In the show notes will be a more complete list of commonly used 17th century salts. It will include both the modern chemical name and their older common descriptive or vernacular names. For this podcast, I'll only be covering the two most common groups of useful 17th century kitchen chemicals that are salts. Otherwise, this podcast will become the boring kind of chemistry class where you're just listening to a list of alphabet soup. No fun. This is just meant to be an introduction, and besides, there are more salts that enter the kitchen in the 18th century and the 19th century, and so on. I can't do everything at once. So, into the 17th century kitchen. There were two categories of salts that I will talk about here, beyond table salt, that were essential parts of the cooking tool set. The first salt set that was of use in the 17th century kitchen was the carbonates, especially potassium carbonate and sodium carbonate. These come from potash, or that white ash in the bottom of the kitchen fireplace, or wherever you were heating your pots. So here's what's going on. When you burn vegetable matter, wood, shrubs, whatever, the carbohydrate part, the carbon, hydrogen, and oxygen, the vegetable matter, literally goes up in gas and steam and smoke. What is left behind is the minerals, potassium and sodium carbonate salts. The white ash from burning hardwoods, that is the deciduous trees like oak, birch, hickory, that kind of thing, is majority potassium carbonate. If you burn one of those halophyte bushes that I talked about, like sea beans or glasswort, which contain lots of sodium, you'll get mainly sodium carbonate. And if you're wondering, well, why not softwoods like pine? Well, there's two kinds of problems. The first is the wood isn't dense enough and doesn't contain enough minerals, and that's where the whole soft comes from, by the way. And second, the resin and saps in it, when they burn with the wood, they make these other chemicals that sort of mess up the process. So when the 17th century housewife ran water through the kitchen ash, that was a matrix holding potassium or sodium carbonate. And when you run water through that, ta-da, lye comes out the other end. Both of the solutions that result from adding water to either potassium or sodium carbonate, sodium hydroxide or potassium hydroxide, are just lumped together and called lye because they were made the same way and they did the same things in the kitchen. Oh, and for what it's worth, yes, the element potassium was named after its kitchen source, potash. So once lye was made from these carbonates, there were two ways this basic solution was used in the 17th century kitchen: to lye treat foods or to make soap. First, lye treating foods. In the American kitchen, that would be the nixtamalization process from the corn episodes. This works because that basic lye is very, very negative. It goes and starts replacing the hydrogens in the corn's vegetable matter, causing it to sort of unravel a bit, which we notice as softening. This would sort of be like my cat picking away at a pair of tights I'm wearing. The longer she does this, the more the tights are going to come apart. So with the corn, that means that tough pericarp comes off, the germ that might sprout in storage is denatured, and the starch inside softens and becomes quite a bit more digestible. The second use of lye in the 17th century American kitchen was making soap, though this was usually done out in the kitchen yard. Fat, which is a different string of carbons and hydrogens and a little oxygen than vegetable matter, would get mixed into the lye solution. The sodium or potassium in the lye, again, shoves in and disrupts the hydrogens, messes up the structure of the fats, and it all comes back together as soap, if I may radically oversimplify. Making soap is something you can do at home even now. I mean, thousands of Etsy sellers can't be wrong. But like cooking, there are things that can hurt you if you don't take precautions. So if you're curious, read up on it. Take all the safety precautions, wear safety goggles, and whatever you do, do not drink lye. Don't even splash it on yourself. Colonists would test the strength of lye by checking to see if it would dissolve a feather. It is not food. It's the stuff people spray on the inside of their ovens to dissolve burned-on food, or pour down their drains to dissolve clogs. Burns from strong basic solutions are no fun. The other important kitchen chemical salt was saltpeter or niter. These are two different names for just one chemical, potassium nitrate. It was popular because it super duper stopped rot. It's more poisonous to bacteria that compete with us for food than regular salt, especially the particularly deadly botulinum bacteria. That's the one with a toxin that is 7 times more deadly than cobra venom. So, saltpeter was a kitchen essential. Oh, and if that name sounds familiar to you for some reason, botulinum toxin. Yeah, that's Botox, which is what people are currently injecting into their faces to paralyze them a little bit so they prevent wrinkles. Shrug emoji, I guess? I don't know. Anyway, when the saltpeter was added to a regular salt brine or a salt rub to cure meat, it would make the meat keep better and longer. Humans are fine with the tiny amounts required to take out deadly bacteria, but too much saltpeter is poisonous to humans. I mean, too much salt. Sodium chloride is poisonous to humans, so, moderation. Which is why when you buy saltpeter, and it comes by a lot of different names now, but if you buy it to make a pickling solution or a salt cure, they always dye it pink, so you won't mix it up with something else. 17th century cooks were able to keep track of the saltpeter because it was a dry, small powder, while the kitchen and pickling salts were bigger chunks, and the bay salt was often a bit damp. Fortunately, if a cook got the ratio wrong enough that it would hurt someone, the food would usually also taste bad enough that people would want to spit it out anyway. Now, I kept mentioning gunpowder. This kitchen saltpeter is the same saltpeter or niter that Chinese alchemists mixed with sulfur and charcoal to make gunpowder. Now, the Chinese alchemist, or probably physician, was actually trying to make a medicine. The original recipe includes honey. But, boy, somebody got a surprise. Anyway, somewhere around the 13th century, gunpowder was transported to Europe through Central Asia and the Middle East. And while it tastes unpleasant in large quantities, it does have a flavor that is similar enough to salt that desperate soldiers who had lacked salt for a long time were known to use a bit of gunpowder to flavor ash cakes or corn mush. Now, disclaimer. Do not taste gunpowder. It is not food. And modern gunpowder is actually quite a bit more toxic than this old-fashioned black powder stuff. This is also not a recommendation that you go and make gunpowder. First of all, sulfur on its very own is toxic. My grandmother used to use it as an insecticide. And this kind of gunpowder is unstable and can literally go off just for no clear reason and break and burn things you like. It's really more trouble than a bored and unattended husky. So by the 17th century, salts were well on their way to being systematized. There were good ways of identifying the useful ones. Identification meant deposits of salts like potassium nitrate or sodium nitrate or calcium hydroxide could be identified and mined. They were easy to keep and trade. So their trades expanded right along with sodium chloride. And once large sources of especially the nitrate salts were in hand, both extra long-lasting salted meat and gunpowder could be produced in quantity. Governments could send out ships for longer voyages with the spiffy new cannons they had to not just find the new world, but to carve out large chunks by clearing away the previous inhabitants and then defend it against other Europeans. Thus, the development of privateers, pirates, convoys, and armadas went hand in hand with merchant shipping and colony ships. So how has that carried over into today? Well, most of the salt made in the world now is still sodium chloride, but barely any of it goes into food. Less than 10%, even if you count all the packaged food. In the U.S., most of the salt mined here is actually used in road de-icing. But the emerging trade in mining chemical salts that really took off in the 17th century would never slow down. It is, after all, much cheaper than making them. Chemical salts now have a role in just about every manufacturing process there is. Metal, glass, plastics, dyes, fabrics, drugs, you name it. That complicated thing about salts and pH, that's now used to stabilize pH and either get things out of solution or keep them in. We're still trying to leave behind a lot of these toxicity issues, but at least the labeling is getting better. The 17th century was a busy time, and we can still see its ripples in our time. But thanks for spending a little extra time on salt. Show notes for this episode will be at thehistoryofamericanfood.blogspot.com. Along with any promised pictures and links, I'll also include any interesting media I consumed for the episode. I'd really appreciate a quick rating or review on your podcast widget to make it easier for people to find the show. Music for this podcast is Fingerlympics by Dr. Turtle, and the link to the show notes is also in the show's Twitter bio at THOA Food and in the show description.